Hello guys, welcome to Physics Grad. This is the third video on canonical transformations, and in this video we are going to see whether there is a systematic way in fact of coming up with the canonical transformations through a particular mathematically valid procedure. Okay, so let us begin. So we'll begin by stating the fact that which we already know. So we know that not all transformations are canonical. So only those transformations which preserve the form of the Hamilton's equations are the ones which we call as canonical transformations. Okay, because not all transformations can preserve the form of Hamilton's equations. Okay, now we ask the following question: is there a way to systematically construct a canonical transformation? Because so far what we have done is we have randomly chosen the transformation and checked whether it is canonical or not. So what I am asking is there any step-by-step way of coming up or constructing this canonical transformation, or should we resort to trial and error? Okay, or should we resort to trial and error, which means we come up with the particular transformation, check whether it's canonical or not, as we have seen in our previous video, or is there a systematic way of constructing a canonical transformation? And the answer to this question is indeed yes, and we are going to see how to do this in this video. Okay, so to see this, consider the Hamilton's principle. Consider Hamilton's principle, which says that for the correct path, our variation in the action given by variation in integral L dt, where integration is from the initial time to final time, should be equal to 0 for correct path. Now, if we write it in terms of the Hamiltonian formulation, this simply becomes in variation of integral pq dot minus h, okay, minus h dt. This is equal to 0. So this is basically a Legendre transformation of the Lagrangian. When we write our Hamilton's principle in this form, this is generally called modified Hamilton's principle. Just nomenclature. That is, when we write it in the form of Lagrangian, we call it as just Hamilton's principle. When we write it in terms of the Hamiltonian, we call it as the modified Hamilton's principle. Okay. From this form, we can derive Hamilton's equations. This also we have seen in our lecture on deriving Hamilton's equation from principle of least action. So, from this, we can derive Hamilton equations. Correct? Now, since our canonically transformed variables, that is the transformed generalized momenta and coordinates, also satisfy Hamilton's equations, but of course with the new Hamiltonian h dash. Okay, this implies we should be able to derive the Hamilton's equation corresponding to these variables from a corresponding variational principle having this form. Okay, so we should be able to derive it from a variational principle where the variation of pq dot minus h dash dt should be equal to 0. I am going to call this equation 2 and call this equation 1. Okay, so this is nothing but the modified Hamilton's principle in terms of the canonically transformed coordinates and momenta, and of course the new Hamiltonian. So this implies for the correct path with endpoint fixed, of course this is a necessary information that we need when we use our Hamilton's principle. So with endpoint fixed, we have the variation in PQ dot minus H dt is equal to 0, which should also be the case with our transformed variables. So this is for the correct path. Okay. Now, does this relation imply whether this quantity is equal to this quantity? No, because we are only considering the variation, not the quantity as such. Okay, so let us note that down. Note, this doesn't mean integral PQ dot minus H dt is equal to integral PQ dot minus H dash dt. Okay, but we can say that they are related in the following manner, that is some constant lambda times PQ dot minus H is equal to PQ dot minus H dash plus a total time differential of some function whose variation should be 0 at the initial and final coordinates. Okay, so variation del f of f must be 0 at the endpoints. Only then it will vanish. And now if we take the integral of this equation, we have integral lambda PQ dot minus H dt will be equal to integral PQ dot minus H dash dt plus integral df. Correct? Now if we find what is the variation, okay, so this in turn can be written as integral PQ dot minus H dash dt plus f final minus f initial, that is the value of the function f at the final coordinates and initial coordinates. So now if we calculate the variation, we have variation of lambda times integral PQ dot minus H dt is equal to variation of integral PQ dot minus H dash dt plus variation of f final minus variation of f initial. But we said that our function f must be such that its variation should vanish at the endpoints, which means these two terms should go to 0. Okay, so this implies that if lambda is equal to 1, then we see that variation in PQ dot minus H dt is equal to variation in PQ dot minus H dash dt, which is what we initially assumed. Okay, so this what do I say? So this reassures the fact that when we take the relationship between this quantity and this quantity in this manner, then we are sure to get this particular relation for the correct path, provided the value of lambda is equal to 1. And this relation is true when the new transformed variables are transformed using the canonical transformation. Therefore, when lambda equal to 1, the the P's and Q's are obtained using canonical transformation transformation, and just for the sake of completeness, if lambda is not equal to 1, then this corresponds to something known as the extended canonical transformations. Extended canonical transformation. Now we are not going to discuss in detail about this because we are just focusing on this, but to be brief, this is basically consisting of a scale transformation, which is basically scaling the coordinates. So this consists of transformations like q dash equal to some mu times q and p dash equal to some mu times p. So basically we are scaling it, and when we do this, the new Hamiltonian h dash will be nothing but mu times mu into the old Hamiltonian. Well, I'm not going to go into the details of this as I told you, and this particular quantity will be equal to lambda. So this extended canonical transformation is going to be a scale transformation followed by a canonical transformation. So when we do these things in sequence like this, we will have lambda not equal to 1, and this is usually used when we want to convert from one units to another, like for example from kilograms to grams or something like that, or in other so the other usage of the scale transformation will be when we take into consideration the relativistic effects, which involves time dilation and length contraction and so on. So when we have time dilation or length contraction, which are relativistic effects and which we are not going to study in this playlist, we will have to use this kind of transformation, contraction. Okay, so when we have these cases, then we have to consider transformations where lambda is not equal to 1. But we are not going to do that. We are just focusing on relations where lambda is equal to 1, and therefore for the transformation capital P and Q to be canonical, we can say that the relationship between this guy and this guy is given by basically this relation. Where is that? So when lambda is equal to 1, this is the relation that we get. Okay, so this will become more clear as we move on. So let us proceed further. Now, for now, we are just going to consider transformation for which lambda is equal to 1. So therefore we have integral pq dot minus h dt is equal to integral pq dot minus h dash dt plus integral df. Okay, now this in differential form can be written as, this implies p dq minus h dt is equal to p dq minus h dash dt plus df. Okay, so basically I am writing the same relation in differential form instead of the integral form, and this is what we get here. Q dot is dq by dt, so when we multiply it with dt, we will be remaining with dq, and that is what we get here. Similarly the rest of the things. So this is the relation that we have in order for P and Q to be obtained from a canonical transformation. Okay, now this implies that our df can be written as p dq minus p dq plus h dash minus h dt. Okay, now this equation suggests that f must be a function of q, capital Q and t, because this is the total differential, and the form of this equation is saying us that we are assuming f as a function of the small q coordinates, big Q coordinates and the time. Okay, so same thing, if we have degrees of freedom greater than 1, this same equation will look like df equal to summation pi dqi minus summation pi dqi plus h dash minus h dt. Okay, so from this we can get the following partial differential equations, which says since f is related to dq like this will be equal to pi. Similarly, dou f by dou qi will be equal to minus pi, and we have dou f by dou t plus h equal to h dash. Okay, so these are the relations that we have, and I am going to call this as equation 3, this as equation 4, and this as equation 5. Okay, so these relations assumes f is a function of qi, qis and t. Okay, now in the relation 3, pi is expressed in terms of qis and t, because here this is a function of qis and t, and when we are just partially differentiating with respect to qi, so the left hand side of this relation is still going to be function of these three quantities. Okay, so this implies we can invert this relation and get our capital Qis as a function of Pis, Qis and T. So what we are just going to do is, so this will be some relation which involves Qi and T, and we are just going to take everything to the other side except for Q. So when we do that, we can get Qi as a function of Pi, Qis and T, which is nothing but our one half of the canonical transformation equation, because at the end of the day, canonical transformation is nothing but being able to express capital Q in terms of Q, P and T, and that is exactly what we are doing here. Okay, so this is the first half of canonical transformation. So what have we done here? If we know what is the form of f, then from this relation we can calculate pi in terms of the old coordinates, new coordinates and time, and then invert the relation back to find the new coordinates in terms of these three quantities, and that will give us a transformation which will have to be necessarily canonical, because we can derive the Hamilton's equation from these relations, and these Hamilton's equations will follow for any Hamilton you choose. That means it will be valid across all systems as well, and therefore this particular relation corresponds to one half of the canonical transformation equations. Okay, so similarly, if you examine equation number 4, which is this relation, here we are expressing Pi is in fact, there will be s number of equation if s is the degrees of freedom. Okay, so I goes from 1 to until s, where s is degrees of freedom. So all the Pi's, this s is basically for plurality. Okay, all the Pi's is expressed in terms of the old coordinates, new coordinates and time. Now we can use, if I call this relation, what relation we get there as relation number 6, we can use 6 here to write Qis in terms of the old coordinates old momenta and time, and from this we have pi's as a function of, so when we substitute for qi's in terms of these things using the relation 6, now we will get pi's as a function of the old coordinates, old momenta and time, which is nothing but the second part of our canonical transformation. So this forms the second half of canonical transformation, correct? And to perfectly end this story, we will use equation 5. So in 5 we can write h as a function of q's, p's and t by writing q's, p's in terms of q's, p's and t's and t by inverting the relations 6 and 7. Here I am going to call this as 7. Okay. So what we are basically doing is that here this h will be a function of the old coordinates and momenta, and by using these two relations we can invert them to find the old coordinates and momenta in terms of the new coordinates and momenta, and therefore write our old Hamiltonian in terms of these new coordinates. And similarly our f also, which is a function of old coordinates and new coordinate and time, here also the old coordinates can be replaced by the appropriate functions of new coordinates and momenta. And finally what we will get is that, so do the same for f, then therefore we get h dash in terms of q's, p's and t, and this we call as equation number 8. So now basically by specifying, or if we know what the function f is, which is a function of the old coordinates, new coordinates and time, then from that relation by using equations 3, 4 and 5 we can get our canonical transformation equations, and not only that, we can even get the relation for our new Hamiltonian h dash in terms of the new coordinates and momenta and time by inverting the equations 6 and 7, which is this and this. Where did I write 7? Okay, this is 7. So using these two relations we can invert them and write the old coordinates and momenta in terms of the new coordinates and momenta, and finally get the expression for h dash in terms of these variables, which solves our entire transformation problem. Okay, so now from this information we have got the canonical transformation equations as well as the expression for our new Hamiltonian in terms of the new coordinates and momentum. Okay, so this implies by specifying the function f of q, q and t, we can generate canonical transformation equations from relations 6, 7 and 8, and the transformations so obtained have to be canonical because they will satisfy Hamilton's equation, because they basically leads to the relations leads to the modified Hamilton's principle in terms of the new coordinates, from which we can derive the Hamilton's equations, which means the Hamilton's equations are preserved under this transformation, and this is valid for any old Hamiltonian, and therefore this is indeed generating a canonical transformation. So this is why, so we will call f as the generating function, because by knowing f we can generate a canonical transformation in this manner. Okay, we will see examples to make this clear in the next video. And just to conclude, so to construct a canonical transformation, all we need to do is define what the function capital F Q T is, which is what we call as the generating functions. Okay, now there are different types of generating functions. We can even have generating functions in terms of the old coordinate, new momenta and time as well, and this will be our topic of discussion for the next video. So thank you for watching. See you next time.